Okay, guys, so we are still working on the second order RLC bandpass filter, which are also called RLC resonant circuit. And this is the series one that we were discussing last week. There is a series RLC resonant circuit and there's a parallel RLC resonant circuit. So the one that we started discussing last time was series, and after the series circuit, we are going to discuss actually lab that you have to do, because that is the application of series RLC circuit. And then we are going to look at the parallel bandpass filter or parallel RLC resonant circuit. So this is what we did before we adjourned the class last Wednesday. We started discussing series bandpass filter. We discussed what is the bandwidth, the difference between the low pass, the cutoff frequency on the low side and cutoff frequency on the high side. Difference between the two is the bandwidth of the filter. And you have the, we did not really discuss, but you have the stop frequency on the low side and upper side as well. You have three bands, of course. You have a pass band where the information is let, the filter let through the information that is coming at its input. And then you have the transition band. Transition band is supposed to be as steep as possible, such that the information or the frequencies that we do not need, they don't go through the transition band. So for the ideal filter, basically, your bandpass response is simply something like this. So this is your pass band, and then you have your stop band. There is really no transition band in your ideal bandpass filter. But of course, for the practical bandpass filter, you have transition band. And again, we want the transition band to be as steep as possible so that it can kind of follow the ideal response. And of course, we have a stop band where the frequencies are stopped and the information doesn't go through the filter. Important quantities that we need to have the mathematical values so that we can design a filter, of course, is are the low pass, the cutoff frequencies at the low side and high side. We need to know what is the center frequency, which is called the resonant frequency. And of course, we need to know what is the bandwidth. Of course, if we know the upper cutoff and lower cutoff frequency, the bandwidth calculation is easy. Then there are other factors which are called the quality factor. Quality factor is basically how selective the filter is to let the information go through. That relates to the quality factor of the circuit. We are going to look at the quality factor and its equation as well. And then finally, we're going to do some example, and then we are going to discuss the application, which is the lab that you will have to do. The lab is only, again, theory and PSpice based. We are not doing lab in class. Again, we don't have time to do lab in class, so it's going to be theory and PSpice based. But it's a really good lab as far as understanding the application of the filter is concerned, as you will see. Okay, so let me move this screen. So let's see, what did we discuss? We discussed the output voltage in terms of input voltage and the three components. Then we wrote down the transfer function. From the transfer function, we wrote down the magnitude response of the function and the phase response of the function. And then we plotted the curve in MATLAB, Octave. We took an example of three values of the component. And from those values, we plotted a curve. Right now, we do not know what is the cutoff frequency. We do not know what is the bandwidth. We just use three values and we plotted all these things. Usually, we are doing the opposite thing. That is, we are setting the filter for specific cutoff frequencies, specific bandwidth and stuff, and then we calculate the values of the component from those. And from the plot, we confirm if our cutoff frequencies are the one that we were setting, if our bandwidth is the same that we were setting, and so on and so forth. So this is where we stopped last time. Let's go ahead and move this here. And then, yes. Yeah, so this is the response of ideal bandpass filter. So you have a stop band on each side and the pass band. But basically, ideally, it goes from the stop to pass band basically at the same frequency, which is not possible in real world because, of course, the components require some time to energize and de-energize, as we know, capacitor and inductor. So you always have a transition band going from the stop band to the pass band. And during those transition band, of course, since remember your goal of a band pass filter or any filter is what pass band should let all the frequencies pass through them. The stop band should stop all the frequencies that you don't need. Transition band is the band where it's neither 0 nor 1. It is transitioning between stop and pass. So you may have some frequencies pass through the transition band that you do not need. The magnitude of those frequencies will be small, but nevertheless, they may be able to pass through the filter because transition band is not entirely stopping those frequencies. So we want the transition band to be as steep as possible, even for the real filters. And that depends on perhaps the quality factor of the filter. The better the quality factor, the selectivity of the filter is better. Selectivity means, of course, how selective the filter is according to the frequencies that you want to pass through the filter. So yes, there is no really transition band in your ideal filter. Okay, let's discuss now. Resonant or center frequency. That is your omega naught or f naught. That is the frequency at the center of your bell curve. So what happens at the resonant or center frequency is L and C starts exchanging their energy, and XL becomes equal to XC. At that frequency, the source only sees a resistive circuit. So XL and XC cancel each other basically at the center point of the bell curve. They start exchanging energy with each other. And since XL is positive and XC is negative, they become equal to their magnitude, that is, become equal to each other. I should write down magnitude, not the sign, of course. The magnitude of XL becomes equal to the magnitude of XC. They have opposite sign. So when they become equal to each other at that specific frequency, which is the center frequency omega naught or f naught, then they cancel each other because they're connected in series. So when you add them in series, XL has, let's say, 5J and XC is negative 5J. They're going to cancel each other, and basically you can replace them by a short circuit. So the source will only see that I have only resistance connected, in the circuit, because XL and XC, they cancel each other. At that time, you get the peak response of the circuit because your total impedance is the minimum value, which is the value of only the resistor. So that's why you see the peak value, the top value, which is the center frequency, as the peak response, because you do not have any reactance. Well, you do have reactance, but the reactances of XL and XC, they are canceling each other. So you only have resistance as seen by the source. So let's figure out what is the value of omega naught. XL is equal to J omega L, and XC is equal to 1 over J omega C or negative J over omega C. So magnitude of XL becomes equal to magnitude of XC means omega L. And now I'm gonna, actually, I should write this down. At omega naught, magnitude of XL is equal to magnitude of XC, which implies omega naught L becomes equal to 1 over omega naught C, which will become omega naught square is equal to 1 over LC, and omega naught is equal to square root of 1 over LC, or F naught equals to 1 over 2 pi square root of 1 over LC, since F naught is omega naught over 2. So this is your resonant frequency. And now, of course, you can see that this is the same resonant frequency as we discussed in the second order RLC circuits in chapter number, what was that, 8. The resonant frequency term is the same, 1 over square root of LC. So when you see the peak value of the frequency response, basically the frequency at that peak value can be calculated using square root of 1 over LC radian per second, or 1 over 2 pi square root of 1 over LC hertz. So one is radian per second, of course, one is hertz. Now the second thing is cutoff frequencies. So let's look at upper and lower cutoff frequencies. So this is omega cutoff low and omega cutoff high or upper, or FC low and FC upper, also called omega C1, omega C2. Now we know that at cutoff frequencies, magnitude of the frequency response of the filter. What is the magnitude of the frequency response of the filter at the cutoff frequency? 0.707. The peak value, 1 over square root. And peak magnitude occurs at DC, that is omega naught, omega is equal to 0. So with this condition in mind, we will figure out from the magnitude of the transfer function at the cutoff frequency magnitude of the transfer function at cutoff frequency should be equal to 1 over square root of 2 at each side, at the low side and the high side of frequency spectrum. So we have 1 over square root of 2, and if we go to, if you go to the magnitude response, this is the magnitude response, omega RC over square root of 1 minus omega square LC square plus omega RC square, and you have it in your notes from last week. So I'm going to keep this window on the other side and use that equation. I'm going to call omega c as the cutoff frequency, and then there will be two cutoff frequencies, of course, since this will be a quadratic equation. So I'm going to assign one as omega cl low side and the other one as omega c high or omega c upper. So omega rc or omega c rc over square root of 1 minus omega c square lc square plus omega c rc square. So all I did is in the magnitude equation that we had last week that I just showed you, we went ahead and equated that magnitude response with 1 over square root of 2, and instead of omega I put omega c, which is the cutoff frequency. And now we're going to find out what value of omega c is going to make the response to be equal to magnitude response to be equal to 1 over square root of 2. So we are going to manipulate this equation. Let's go ahead and square both sides so that we can get rid of square root 1 over this. So let's write down 1/2 is equal to omega c rc square, and likewise we get rid of the square root on this side as well. 1 minus omega c square lc plus omega c rc square. And then we manipulate it, cross multiply. 1 minus omega c square lc square take this omega c rc square on the right side, and we have 2 omega c rc square. That's gonna subtract this term. So on each side we're gonna have 1 minus omega c square lc square is equal to omega c rc square. Take a square root of both sides to get rid of the square term, and we're gonna have 1 minus omega c square lc equals plus minus omega c rc. When we take the square root, we're gonna add a plus and a minus sign. So now I can write two equations. Equation 1, 1 minus omega c square lc plus omega c rc equals 0. When I take this on the left hand side of the equation, right hand side is going to become 0. And my equation number 2, of course, is going to be with the opposite sign. 1 minus omega c square lc minus omega c rc equals 0. Both are quadratic equation as far as in terms of omega c. So both are going to give us two roots. One root is going to come from, one frequency is going to come from one equation, either high pass or low pass, and one frequency is going to come from the other equation. So let's look at those two frequencies. Let's call this equation number 1, and let's call this equation number 2. So from equation number 1, let's rearrange the term, because omega c, of course, is what we are looking for. So we're gonna change the sign of omega c. We're gonna multiply both sides by -1. So that's going to become omega c square lc minus omega c rc minus 1 equals 0. And then we are going to divide the equation by LC so that omega c square has a coefficient of 1. So omega c square minus omega c divided by LC. C and C will cancel each other. So I'm going to have R over L minus 1 over LC equals 0. And observe this is quite close to the equation, characteristic equation of RLC circuit that we discussed. Instead of omega c, you put S. So it's going to be S square minus R over L S minus 1 over LC. That's the characteristic equation of the RLC circuit, from which we derive the three cases: underdamped, overdamped, and critically damped circuits. So they're very close to each other. One we are studying, of course, in the frequency domain. The other, of course, S actually is the Laplace variable. Yes. Yeah. S. Mhm. Yeah, S is a Laplace variable. S is basically has both transient response and your steady state sinusoidal response. Right now, we are just looking at the steady state sinusoidal response because we have only omega and we don't have sigma, which is the transient variable. Okay, so from this equation, we find the roots of the quadratic equation. So omega c will give us negative b, so R over L plus minus square root of b square, so negative R over L square, so R over L square, minus 4ac. So minus 4, and a is 1 and c is negative 1 over LC. So I'm going to put down plus 4 over LC divided by 2a, so divided by 2. And these are lower, no, actually not lower number, sorry. This is just two roots, 1 and 2. Of course, we have two roots. I'll come back to that. We call them 1, 2, 1, 2. Take this 2 in the denominator of the numerator, So we're going to get R over 2L plus minus, take the 2 inside the square root. That's going to become 4. So R over 2L square plus 1 over LC, because it's going to be 4 here in the denominator, and this 4 is going to cancel each other. Okay. All right. So from this, we have two roots. Omega 1 equal R over 2L plus R over 2L square plus 1 over LC, and omega 2 equals R over 2L minus square root of. And from this, we are going to get our upper cutoff frequency, which is this one. I'm sorry. The frequencies cannot be negative, remember, right? The frequencies has to be positive values. It cannot be negative values. So this is going to provide a positive value right here. Okay. So one frequency is going to come from the first quadratic equation, which is now the upper, which one we did review? Yeah, the first one, right? So the first quadratic equation that we rewrote like this. And the second is going to come from the second quadratic equation, which will be lower cutoff frequency. From equation number 2. So now we rewrite this equation like we did this one, multiply both sides by -1, and then divide by LC. So we're going to have omega c square plus r over L omega c minus 1 equals 0. So that's coming from this equation. Again, we did the same thing like we did over here. Multiply both sides by -1 and then divide both sides by LC to get rid of the coefficient of omega c square. So the only difference between the two is this plus sign over here. And once again, we're going to find the roots negative r over L okay. So now we have again two roots. and which one we are going to choose? The one that is going to give us, of course, positive frequency. And that is going to be negative r over 2L plus square root of r over 2L square plus 1 over LC, because if we have both negative sign, of course, the frequency is going to be negative. So here we're going to get our lower cutoff frequency. Omega cutoff lower is negative r over 2L plus square root of r over 2L square plus. So this is our upper cutoff frequency with the positive sign here, and this is our lower cutoff frequency with the negative sign here. So we can write down omega lower omega cutoff lower, or let's write down upper first. Upper cutoff lower is simply r over 2L square plus 1 over LC plus minus r over 2. So these are the equations to calculate the lower and upper cutoff frequency. Make sense so far? And again, if you want to calculate the cutoff frequency, or if the cutoff frequency is given in hertz, then you have to divide both sides by 1 over square root of 2 to get frequency, cutoff frequency in hertz. Bandwidth omega cutoff upper minus omega cutoff lower. So when we subtract omega cutoff upper or omega cutoff lower from omega cutoff upper, what you're going to get, of course, this factor is same in both equations. So when we subtract this factor, square root is going to cancel each other, and we are going to get r over 2l minus negative r over 2l, that is 2r over 2l. So the bandwidth is r over l, and remember this is radian per second. Radian per second. And of course, bandwidth in hertz is going to be 1 over 2 pi r over l. So this is bandwidth in radian per second and bandwidth in hertz. Center frequency or resonant frequency can also be given in terms of cutoff frequencies. We know that the resonant frequency is 1 over square root of LC, as we discussed here. 1 over square root of LC. So if we take omega C lower and omega C upper product and take the square root of that, you will end up with 1 over a square root of LC. I'm not doing the derivation, but it's easy to do the derivation here. Multiply the two roots together, and you will see that you're going to come up with 1 over a square root of LC, which is your resonant frequency. So resonant frequency can also be calculated if you know the center frequencies. I mean, if you know the cutoff frequencies, then you take the product of the center, the resonant, the cutoff frequencies, and take the square root of that. All right, what is quality factor? Quality factor is basically selectivity of the filter or, in other words, it's the width of the pass band. How selective the filter is during the pass band, that is represented by the quality factor. Selective means if it will be more selective, that means it's going to let only the frequencies that you need pass through it. And if it is less selective, it is also going to let some other frequencies pass through it that are in the transition band of the circuit. So we want the filter to be very selective. That means we want the width of the pass band to be Well, basically, we want it to be very steep, the transition band to be very steep, so that width is equal to the bandwidth of the filter outside the cutoff frequencies as well, close to the bandwidth of the filter. Just to give you an example, let's say we have two filters. F. Oh. All frequencies are positive. I'm just going to show lower frequencies on the left side and then upper frequencies on the right side, but all frequencies are positive. This is starting at 0. Let's say you have a filter, bandpass. Something like that. This is your center frequency, F0. This is FC low and FC. Now, for this bandpass filter, you can see that outside the two cutoff frequencies, of course, the bandwidth is measured between the two frequencies. But outside the two cutoff frequencies, you have decent amount of transition band. And some of the frequencies can pass through those transition band from here all the way up to here, where the stop band will start. Therefore, the selectivity of the filter is not as good as you want it to be. Now, same filter you can have with the same bandwidth, but with better selectivity. Something like that. So now you also have another bandpass filter, and it has the same bandwidth, because bandwidth is from the cutoff frequencies, between the two cutoff frequencies. But now the transition is not as wider, so the width of the filter is not as wider as the other one. And then you can have another filter, of course, that can even be sharper. That can go something like this. Something like this. So although the bandwidth of each filter is the same, but the difference is width of the filter or the transition band of the filter, that's different from for each one of the filter. So the sharper the filter transition band is going to be, that is, it is more selective. It is not letting the frequencies within the transition band, like for example the blue one, it is not going to let the frequencies outside the bandwidth, many frequencies, pass through them. There are a few frequencies that will pass, but this is going to let more frequencies pass, and this is going to let a lot more frequencies pass through the filter when the input is coming, and you want only the selective frequencies to be at the output. So more selective filter means, with a higher quality factor, means how tight it is around the bandwidth, basically. That's define the selectivity of the filter, and that defines the high quality factor of the filter. So the blue one has the highest quality factor, and then the red one, and then the green. So quality factor of blue is greater than the quality factor of red, which will be greater than the quality factor of the green filter. So hi, yes.
So the quality factor also has a direct.
Well, we always try to mimic the response of ideal filter, right? We cannot, even theoretically, we cannot go into the detail why, but even if you do the theory work, you cannot basically get to the ideal filter response, because if you want to get to the ideal filter response, your response is going to start before your time response of the filter is going to start before t is equal to 0, which is not possible, right? Even theoretically, again, we're not going into the derivation. But yes, that's the objective. The objective is to go as close as possible to the ideal filter response. And that happens usually, especially when you are creating higher order filters. Then your response curves, your transition band is getting steeper and steeper, especially active filters. You're increasing the order of the active filters. And again, most of you are going to take integrated circuit. You're not going to take integrated circuits. Your computer, you're going to take integrated circuits. And who else is computer concentration here except Lazaro? All of you are electrical. So all of you are going to take integrated circuits. Most likely I'll teach that, or Dr. Hall will teach it, whoever, next spring. So in that, we're going to study the active filters, active bandpass filters, active low pass, bandpass, high pass. So there you will see, actually we discussed low pass. I think we discussed low pass and high pass, maybe not bandpass. But anyways, you can get the idea from low pass and high pass, that when we increase the order of the filter, so we add more operation amplifiers, then that transition band is getting steeper and steeper. The circuit starts becoming complicated, but it starts becoming more selective. In this case, we will still be doing the second order filter, but we can change the component values to get more selectivity out of the filter. Okay, so how do we calculate mathematically the value of Q, quality factor? So Q is calculated as 2 pi times maximum energy that can be stored in the circuit divided by total energy lost per period. Of course, the energy storage components are two, which is inductor and capacitor. Resistor cannot store energy, of course. So maximum energy is stored in inductor at any time and capacitor at any time. We want to know that energy stored in inductor and capacitor maximum, and energy is lost in the inductor. That's the component that loses energy in terms of heat dissipation. So total energy lost in the resistor per unit time, per period can be calculated as the power dissipation in the resistor times T, because power is work over time or energy over time. So energy, total energy lost, is the power dissipated in the resistor times one time period. And I'm not going to go into the complete derivation of that. I'm going to jump to the results. So after some manipulation, we will get the value of Q to be magnitude of the reactance of inductor at the resonant frequency, because the maximum energy is stored at the resonant frequency at the peak value, or where the curve has its peak value, divided by R, which we can write down as omega naught L. Omega naught is the center or resonant frequency, over R, and L over R, or let's go, I'll go back to that. Bandwidth, as we can see, bandwidth is R over L. So we can also write down the quality factor as omega naught times 1 over B, because B is R over L. Omega naught over 1 over B. Since at the resonant frequency, magnitude of the reactance of the inductor is equal to magnitude of the reactance of the capacitor, then we can also write down the quality factor in terms of the capacitor instead of inductor. Xc naught over R, 1 over omega naught Rc. So quality factor can be calculated by either of these equations. Cutoff frequencies can also be given in terms of quality factor and the center frequency. So let's look at that. Cutoff Q and omega naught. We know the two cutoff frequency, omega C upper and C lower, they are given by R over 2L square plus 1 over LC plus minus R over 2L. This is what we derived earlier. So we can write this down as omega C upper, omega C lower. Bandwidth is equal to R over L, so we can write down this as bandwidth over 2. Actually, let me do Q, B, and omega naught. We can either give it in B and omega naught or Q and omega naught. So R over L is bandwidth, so we can write down as bandwidth over 2 square, and 1 over LC is omega naught square. And likewise, R over L is B, so we can write down as B over 2. So that's another equation to calculate the upper and lower cutoff frequency in terms of B and omega naught, bandwidth and the center frequency. Q is equal to omega naught over B from here, since Q is equal to omega naught over B, which implies B is equal to omega naught over q. So we're going to go ahead and plug that value of b in this equation and write this down in terms of omega naught and q. Omega naught over 2q square plus omega naught square plus minus omega naught over. And this is yet another form of lower and upper quarter frequency in terms of center frequency and the quality factor. So you can use any of the formula based upon whichever at the time is easy to use, that is which value you know. But in general, if I'm using it upper and cutoff, lower cutoff frequency, and if I have the values of R, L, and C, then simply I use the values of R, L, and C and calculate the lower and upper cutoff frequencies. But any of these formulas can be used. So these are all the equations that relate to the series bandpass filter. Different terms, different equations, but the basic equations are the ones that are important in terms of R, L, and C. Now let's go ahead and work on a problem. Do it on the next page. A series bandpass filter as R is equal to 10 kilo ohm, L is equal to 50 millihenry, and C is equal to 1 nanofarad. Calculate center frequency, lower cutoff frequency, upper cutoff frequency, bandwidth in hertz, and the quality factor. So again, we have to use formulas and then calculate all these things, and then we're gonna draw the response of the filter and then check the bandwidth on the filter, check the lower and upper cutoff frequency of the filter, and all those things. So R is 10 kilo ohm, L is 50 millihenry, and C is 1 nanofarad. All right, so we know that omega naught is 1 over square root of LC, center frequency. So F naught is 1 over 2 pi square root of LC. So F naught is two times pi times square root of L times C and reciprocal of that, which is giving us 22.5 0.08 kilohertz. F naught is 1 over 2 pi. This is the center frequency. Lower and upper cutoff frequencies. Lower cutoff frequency, once again, 1 over 2 pi, because we have the omega CL and omega C upper equations. Square root of R over 2L plus 1 over LC plus R over 2L. Square root of R over 2 plus 1 over C plus R over 2 divided by 2 pi. Getting incorrect result. Let me go and check the equation real quick. So, R over 12 square. Okay, that's I put R over 12. R over 12 is R over 12 is still getting incorrect result. Let me see. R square over 2L square plus. I'm getting a low frequency which is higher than the cutoff frequency, the center frequency. Let me do it again. So FCL is equal to square root of A square plus square plus A divided by 2. Oh yeah, that's the upper. That's right. That sounds like not the lower. It's the equation for the upper because we have both positive. So this is, that makes sense. So this is 43.48 kilohertz. And the lower is going to be, of course, lower than the center frequency, FC lower. So this I can do FC upper, and this I can make FC lower, part 3. And that is 11.65 kilohertz. Bandwidth is FC upper minus FC lower. .83 kilohertz. And finally, the quality factor can be calculated as simply R over L, or L over R rather. R over L. Omega naught L over R. Omega naught would be okay. Omega naught L over R. R over L is the bandwidth. Omega naught L over R. Q is equal to 0.707. These are all the values. Quality factor is quite small. That means the curve, the width of the filter is going to be large. And now to plot this, we know that center frequency is 22.508 kilohertz, lower cutoff is 11.65, upper is 43.48. So you want to plot it, of course, beyond 43.48 kilohertz, maybe much larger than 43.48 kilohertz, because remember, at 43.48 kilohertz and 11.65 kilohertz, well, we look at the higher frequency. At 43.48 kilohertz, you have magnitude of 0.707. So if you keep increasing the frequency, magnitude is going to start going down. Quality factor is quite low. That means width of the filter is going to be large. So I will go at least up to, let's say, 500 kilohertz at least to plot it. Yes. Is a quality factor, can it be 1, you're saying? It can go higher than 1. Yeah, it's not between 0 and 1. It can go higher than 1. Yeah. Okay, so let's plot it. We did the plotting last week, code and everything. Of course, we discussed that. Plotting is easy. So, yes. Yes, go ahead. Yeah.
I used to try a different one and
Mhm. Okay.
that we did for cutoff frequency.
Okay.
Are we supposed to get the same values as we use in one equation for another?
Yeah, because the equations are coming. So you have the basic equation in terms of R and L, and then all the other equations are derived based on that. Yeah.
So
You got the bandwidth, you got the same.
So, I got the same
Yeah.
bandwidth, I got the same resonant frequency, same quality factors on my port.
Upper and lower is different.
Even though I got everything else.
Well, check how you're entering. I'm assuming it should be the same. It should be the same. Yeah, it's because all of them that we derived were in terms of radian per second. So just make sure to divide it by 1/2 pi. Okay, so go to the last lecture because we do have the equation here. Let's go back. Right here. So we have the magnitude response equation here. We don't have the phase response equation, but this is your, we can go back to the last week and then see what is the transfer function equation, because we're going to plot the transfer function, magnitude response, and the phase response. So let me move this then. This is our last week. And this is what we have for our transfer function. H j omega is equal to j omega RC over 1 minus omega square LC plus j omega RC. So we're going to use this equation. And we have our L and C values already. And we're going to go for omega range. I'm going to multiply 2 pi, whatever f range we are thinking about. So if you're thinking about 500 hertz, I'm just going to multiply that by 2 pi, 500 kilohertz. So I will start my omega from, like we did last time. I don't know, what did we start from, 0.1 or something? So 0.1 or 10. Let's start at 10. Yes. Yeah. Give me just 1 second because the equation is here. I won't be able to see the equation. So let me write the equation first. But the code, Vanessa, is in the last week's lecture. So if you have that lecture, or if you just go to Canvas and look at that lecture, the code is there that we use is the same code. Why I keep calling you Vanessa? You're Gloria now. For some reason, I keep calling you Vanessa. You might just change your name. All right, so we're going from omega value. F value. Made a mistake. F value we are going from. Initially, we are going from, again, if that value is, we can always change the range. So F value we are going from, I'm starting at 10 hertz and going up to 500 kilohertz with the interval of 10. And then omega is defined over F. So 2 times pi times F. And then I'm going to write down my H. H is equal to I times omega times R times C. One minus omega square times L times C plus I times omega times R times C. Okay. And then magnitude of H is equal to the absolute value of H. And phase of H is equal to angle of H times 180. Okay, so this is so far what I have. Put you in front of. So I defined, of course, the frequency range first, starting from 10 up to 500 kilohertz with an interval of 10. Then I defined my angular frequency over f, 2 pi f. And then I wrote down the equation for my transfer function. Then I'm calculating the magnitude of that using absolute value, and then phase of that using the angle function. And now I'm going to plot using semilog x. So let's do figure 1, semilog x. I'm going to do f comma magnitude of h, increase the line width to 1.5, let's say. X label is f in hertz, and y label is magnitude of h of jf. I do. And then I'm gonna run the grid. All right, let's see. Syntax error, semilog x f, and with the h, line width 1.5 x label. Oh, okay. Missing a quote over here. Okay, taking long to print it. I think I'm taking more values, and observe that it still is not gone down to 0. So perhaps I have to increase my end frequency. So let's go ahead and increase the end frequency from 500 kilohertz perhaps to, this is 1 megahertz right here, I think. So let's go ahead and increase that to 2 megahertz maybe. So let's increase, start at 100 hertz, interval of 100, and then go with 2 megahertz. 2 exponent 6. Omega h, magnitude of h, phase of h, figure 1. Okay, all right, maybe better. So the magnitude response, although I'm starting at 100, but again, you're going to start at 10 as well. And again, if you want to go further, you can go to 10 megahertz so that it will be centered and stuff. And it's the same thing. I mean, you can see the curve anyways. So, but if you want it to go all the way down to 0, perhaps just plot until 10 megahertz instead of 2 megahertz. That might look nice per se. So if I go and increase that, I don't think it's going to take that long. So increase this to 10 megahertz. omega H magnitude, phase, and figure. Yeah, looks kind of nice. Center frequency 22.3 kilohertz. Is that what we got approximately? This center frequency 22.5 kilohertz. So again, your mouse is not exact, but center frequency here somewhere. It's 20, 23, 24, whatever, 22.5 kilohertz, whatever is that. 43.48 kilohertz is this. This is my center frequency approximately. 22.5 kilohertz. This is hiding it, annotated. And then 22.5 kilohertz center, and then I have 0.7071 Y value, 0.709, 707 somewhere here, and the X value is 11.48 kilohertz, which is the lower cutoff frequency. I think that's what we got, 11.65 kilohertz. And on the upper side, again go to 0.707 somewhere here. And then 42.7 kilohertz. So we have 43.48 kilohertz. Again, on the curve, of course, it's very hard to pinpoint your cursor. That's why MATLAB is good, because it goes along the curve. Your cursor goes along the curve. In this way, in this Octave, you have a free moving cursor. So all the values can be confirmed from the curve. Your lower cutoff, your upper cutoff, your center frequency, all of these can be confirmed from this curve. Let's copy this and let's go ahead and paste it along with the code. Let's put the code first. This is the code, and then the magnitude response is this. Go ahead and plot the phase response as well and see how does it look like. This is the magnitude response. And then let's plot the phase response as well. Figure 2. Seeing log X, F, phase of H, angle phase response. Their phase response is coming out to something like this. So that's the code to plot the response of the filter, and these are the responses. All right, we are going to go ahead and take a break now. Let's go ahead and stop recording. So the quality factor, since it is evaluated at the resonant frequency, XL naught and XC naught, so they're just calling the quality factor to be Q naught. To represent that, it is evaluated at omega naught. That's the variable that they're taking in the textbook. So I'm just going to go with that, Q naught, to be consistent with the book. Okay. Let's do another problem. This is from your textbook. Okay. The problem is a series resonant circuit has a bandwidth of 100 hertz. With bandwidth of 100 hertz. And contains a 20 millihenry inductor and 2 microfarad capacitor. L is equal to 20 millihenry and C is equal to 2 microfarad. Determine your center frequency, quality factor, input impedance at resonance, and the upper cutoff frequency. Determine F naught, Q naught, Z input at resonance, F1 and F2. F1 is, just since we're calling it low and upper, I'm just gonna call it F cutoff lower and F cutoff. Another thing that I observed, that I totally forgot actually, is we determine the exact equations to calculate the lower and upper cutoff frequencies. There are also approximate equations. If the quality factor is high, then you can approximate the cutoff frequencies. So let's say the cutoff frequencies are here, 0.70. Let's say this is somewhere in the middle. So this is, and this is the other one. So let's say these are two cutoff frequencies, FC lower and FC upper. And this is the bandwidth of the filter. So if quality factor is high, then if Q naught is large, then we can approximate FC lower as F naught plus half of the bandwidth, and the upper cutoff frequency to be the center frequency minus, this is minus, sorry, lower cutoff frequency is minus half of the bandwidth, and the upper cutoff frequency will be plus half of the bandwidth in hertz. And of course, you can do the equivalent in radian per second. So this is the approximation. And this approximation is fairly consistent with the exact values if the quality factor is large. So if the quality factor is large, then of course your width is going to be, it's not going to be very wide. So the bandwidth, half of the bandwidth, you can add or subtract in the center band, in the center one, and you can get the upper cutoff and lower. Yes. It's a good question. I don't think I have answer for that because I think it may be centered. I think, or maybe not, because if it is centered, then you don't need the high Q value to calculate, to do the approximation. So yeah, it is possible that you have a curve like that. Let's say this is the highest point, and then you have something like this. So it is quite possible, yeah. I have seen bandpass filter with characteristics like this. So one side is closer and the other side is wider. Okay, going back to our problem number 2, series resonant circuit. So let's go ahead and start. Yes, go ahead. It is not centered. Okay. I mean this. Oh, you're talking when you're calculating the approximate? From the center point. Okay. Yeah, so that's possible, that means. So if you calculate the approximate lower end cutoff frequency, then it's possible that since the Q value is a small 0.7, then it may not be equal to the exact values that we calculated, 43.48 and 11.65. Yeah, that is true, because you have lower at 11.65 and this is 43.48. So it's not 22 minus 11 is 11, and then 43 minus 22. Yeah, you're right, it's not central. It's not central. So that means if you, because the Q value is so small, 0.7071, if you calculate that approximation, then it's going to be quite different than what we calculated. 22.5 divided by 2, which will be 11.25, plus the center frequency. Bandwidth is 31.83. So 31.83 divided by 2, about 16 or 15.6, plus 11 plus 22. So 15 plus 22 is 37. That's going to give you upper 37 instead of 43. And then 15 or 22 minus 15, 7. So it's going to give you quite different approximation. And the reason is that your Q is quite small over here. But if your Q is large, then it may give you the approximate value, and the exact value may be close to each other. Yeah. So we can calculate that for some problems and see if Q is large, then how close it is going to come out to. Okay, going back to this problem, B is 100 hertz, so a small bandwidth, and L and C value is given to us. Determine F naught, so we can easily calculate the center frequency. Since F naught is 1 over 2 pi, square root of 1 over LC. So F naught is square root of LC times 2 times pi, reciprocal of that. 795.77. That's the center. Q naught. Q naught is magnitude of the reactance over, what was that? Magnitude of reactance over R. Keep forgetting. Q naught is magnitude of reactance over R. And we don't have R, so we have to go to the other value with the B, omega naught over B, whatever is that. Omega naught over B, omega naught over B. It's equal to omega naught over B. Oh, there. I think I did not delete anything that is important. Okay. So 7.95. So it's pretty large, approximately 7.96. So this one is pretty large, Q naught. So we can calculate the exact and approximate values of lower and upper cutoff frequencies to see how close they are for this circuit. Number 3. Impedance value at resonance, the input impedance at resonance. What happened? What happened? Yes. XL naught over R, which we can also use omega naught over B. You're getting something else? Okay. So series resonant circuit, and we are trying to figure out what source is going to see at resonance. Z input at F naught. Now we know what source is going to see at resonance, right? It is. We know what it is going to see at resonance. Yeah, but total impedance. Yeah, so it is going to see only R because XL and XC, they're going to cancel each other, right? So it's going to see only R. Now, we do not have the value of R in this case, but we can figure out the value of R first, and then we can find out. What is the value actually by calculating XL and XC. So let's see, go back. So we know the value of Q, we know the value of omega naught. So with Q, we can find out R value XC naught over Q. or XL naught over Q. So Z in equals R at resonance, since magnitude of XL naught is equal to magnitude XC naught. And Q is XL naught over R, which implies R is equal to XL naught over Q naught. So we calculate the value of R. R is equal to 2 times pi times F naught times L divided by Q naught. 12.566. $12.57. Yeah. No, well, XL naught is 2 pi F naught L. XL naught is 2 pi F naught L. So you have to use the reactance formula, right? Q is calculated whether so Q is a ratio, remember, right? So if we go back and look at this equation, omega naught over B, if you are keeping omega naught and B in radian per second, then omega naught is 2 pi F naught, and B is also in radian per second, 2 pi times 100 hertz, because B is 100 hertz. So 2 pi and 2 pi, they're going to cancel each other anyways. So whether it is in radian per second, both quantities, or hertz, since it's a ratio, it's the same result that you're going to get. All right, what is the fourth part is upper and lower cutoff. And now let's go ahead and calculate both exact and approximate upper and lower cutoff frequency. So first, exact cutoff frequencies. F cutoff lower is square root of R over 2L square plus 1 over LC minus R over 2L. And 1 over 2 pi, because this is in radian per second. So 1 over 2 pi. Okay. So FCL is square root of A square plus omega naught square minus A divided by 2 times 747.34 hertz. And the upper cutoff frequency is the same formula, except you're gonna use plus R over 847.34. So again, the difference you can see is 100 hertz, which is the bandwidth. Now let's look at the approximate cutoff frequency and see how close they are since our Q value is high. So FC lower is F naught minus half of the bandwidth. And this is approximate, so I'm going to use approximation sign. FC lower approximate is F naught minus B over 2. And that's 745.77. And FC upper is going to be 845.77. So instead of 847 and 747 exact value, we have 745 and 845, which are not that far from the approximate value. So the exact and approximate values of the cutoff frequencies are very close, since the quality factor is quite large.
There is a large approximate should be plotted, right?
Plot, the plot is for the curve, remember?
Yeah.
No, but plot is coming from your transfer function.
Oh.
Right? So when you're plotting from the transfer function based upon how many points you're plotting, if you are trying to figure out from your curve what is your cutoff frequency, that depends, again, if your step size is 100 hertz or 10 hertz. The smaller the step size, the better you can track the exact value of cutoff frequency. So it's not going to skip. Like if I'm keeping 100 hertz between each frequency step, then it's possible that I have for this one, since my cutoff frequencies are small and bandwidth is small, I may go for a smaller step size for this. But if my cutoff frequency and bandwidth is large, like in the previous problem in kilohertz, like 20 kilohertz, 30 kilohertz, then I can increase my step size because I may not lose a lot of information. In this case, if I keep 100 hertz as my step size, I will lose a lot of information because it will only plot like 20 points, 30 points, and between each of the points 100 hertz. So I may jump from like 700 hertz to 800 hertz, and I may miss that point altogether, right? So when you're plotting it, you have to be careful about all these facts, that what should be the step size and all those things. One more thing I want to do here, which is very important, is So when you have a circuit like this, of course, it's a sinusoidal circuit, and it is operating at some frequency omega, then you need to figure out what is the value of the output at a certain frequency from a filter. If it lies in the pass band, it is outside the pass band, wherever it lies, you have to find out the exact value of the frequency given an input value. So let's do an exercise based on that, keep the same values for this circuit, and then extend this problem a little bit. For the same circuit, V in is 20 cosine of let's see, 740. Okay, so omega is 2 times okay. Two cosine 1000 pi. Okay. Input voltage is given as 20 cosine 1000 pi t. Determine the value of V out. Now, if a filter problem is given to you, remember your output is equal to transfer function times the input in a filter. So if you figure out what is the value of the magnitude of the transfer function and the phase of the transfer function at the frequency at which the circuit is operating, which is in this case is 1000 pi radian per second or 500 hertz. Make sure you take the correct frequency, whichever omega is 1000 pi, f is 500 hertz. So whichever frequency you are using in the calculation, make sure it has to be correct frequency. So generally, when we are calculating for filters or circuits operating in the frequency domain, we use transfer function. So since h of j omega is V out j omega over V input j omega, then V out j omega is h of j omega times V input j. That's a magnitude and phase. So I'll keep, instead of magnitude, I'll keep that. The transfer function in general is equal to this. And then we figure out what is the magnitude and phase of the output at that frequency, which is 1000 pi, to calculate the output. This implies V out j 1000 pi is equal to h of j 1000 pi times V input J 1000. Remember, input in this case is 20 angle 0. So this is 20 angle 0 or 20 simply. And we have to find the value of H, and that will give you the output. So, of course, since it's a series bandpass filter, we know. So let me do, I don't do clear actually. CLC. And my omega is 1000 times pi. And my V input is 20 angle 0, so I'll just keep it 20. And then my H, let me go back and grab my H. Okay, this is my H. Of course, we already have the values of R, C, and L for the new one that I put. I don't think I cleared those values, right? Let me see. R, L, let me see. 12.566, L is 20 millihenry and 2 microfarad. So these values are here. These are the values that we calculated, I'm assuming, or we have. 12.57 and 20 millihenry and 2 microfarad. So we have all these values. Okay. So all I need to do is go back to my H equation. H is this. And calculate H for that omega 1000 pi. And the value is 0.017673 point that. So let's go ahead and, or we can just calculate that magnitude. Magnitude of H is equal to absolute value of H. And angle of H equal to angle of H times 180 by 0.1294 angle 82.567. So 0.1294 angle 82.567 times 20 angle 0. So V out, mag of V out is equal to 20 times, or VI times magnitude of H, 2.5873. 2.5873 angle 82.5. Let me write down here. So 58 angle 82.56 volt. Therefore, in time domain, the output voltage is given by 2.58 cosine. What was that? 1000 pi? 1000 pi plus 82.56. So if you know the transfer function of a circuit, and most of the time when you are dealing with filters, you know the transfer function. So if you know the transfer function, you can calculate at any frequency for any input, you can calculate the output at that specific point, both the magnitude and the phase values. Output, as you can see, is smaller than the value of the input, 2.58, because the circuit is operating at 500 hertz that means it is operating below the cutoff frequency. At cutoff frequency, remember, it's going to be 0.707 times the input magnitude, right? So 0.707 times 20, so about 14, it's going to be about 14 volt at the cutoff frequency at 745. But now this circuit is operating below cutoff frequency at 500 hertz, and that's why the magnitude of the output is even smaller, which is only 2 point something volt. It is operating in the transient band. So even though we do not want this magnitude to pass through the circuit, but it's in the transient band and the magnitude is still passing to the output. 2.58 is the output. In the ideal case, we want this to be 0 at 500 hertz. Okay, the time is 11:23. So what we are going to do quickly, we are going to look at the next lab. I can stop the recording.